page definition of concavity. Sorry about that.
You see a little piece of chalk.
All right. So I cut the person who draws all the time.
Ooh.
Smart. Could you please erase that? She said yes. She said, yes, I'll erase it. So if you missed the art, I'm sorry. I was just like, we need to clean before we get in there. So, and today we'll be wrapping up 4.1, which dealt with those max and mins just over a certain range of values, maybe from x equals -1 to -2, a certain domain. And then we'll jump to 4.2 and actually get into 4.3. So that's what we're doing. 4.1 is still just this idea of we've introduced what are critical points, max and mins, and we'll get to 4.2 mean value theorem. All right, and 4.3. Concavity, increasing, decreasing. Relative maximums. We'll hit all those topics. So, but before we wrap up 4.1, does anybody have a question on a problem? Oh, cool. 4.1, that was neat because you're finding these critical points. It's one of the problems. So that you might find quite interesting. But these, we did find the max and mins. Oh, let's see. Okay, we'll move into 4.2 then. Yeah, 37. But anyone, if you had questions later on from 4.1, let me know. There's some graphs in there, but when you get to 4.3, the graphs return. So I'm gonna wait today until we get to 4.3 before I put the graph down. And we analyze graphs. We'll analyze graphs, first derivative graphs. We'll take that first derivative graph to be able to get an idea of what's going on with the original function. Okay, so recap, critical points. What's the definition of a critical point?
Critical point is that you take the derivative
Good?
and then you enter the points, right, to see if they are over there or not.
That's right, and it's somewhere on this sheet. If you're like, man, what's a critical point? It's just like, this stuff has so much information on it, you can look through it. You go, where is it? You'll find it somewhere. Do you see it?
Derivative equals 0 or doesn't exist.
There you go. First derivative determines critical points. All right. A critical point is any point in the domain where f prime is equal to 0, f prime does not exist. All right. But also, you know, today, first derivative, as we already know, finds max and mins in intervals of increase and decrease. So when I'm saying we already knew first derivative found the max and mins, we haven't talked about increase and decrease intervals yet. Okay? And so, before we get into some of those problems, because they really come up in 4.3, let's look at 4.2 with the mean value theorem. sometimes it's nice just to see an image of a graph and then talk our way through it. Understand something like the mean value theorem. F minus 12x plus 3x squared. Cool. If anybody has your textbook, everyone, this is on page 288, 4.2. What's the range of the values going from? 1 to what?
3.
1 to 3. I'm gonna take it from 1 to 5.
Okay.
Cool? I'm gonna go from 1 to 5. And afterwards, we'll back up and do 1 to 3. So this is like, just like number 1. From 4.2. In the textbook. It's on page 288. Well, we'll look at this function. And we're going to apply what's called the mean value theorem. And we'll put the mean value theorem on the board, even though I got on that sheet. We'll write it all out, we'll make sense of it. What's that graph look like? I love it, yeah. You got a parabola there, right? And so what's going to go on with this thing, you're going to get some kind of parabola. Maybe it's like this. And between these 2 points, let's say here's where x equals 5. And maybe here's where x equals -1. Or excuse me, x equals 1. So it could be different. But this could be any function. What we're saying is, can you imagine the slope of the secant between these points? Wouldn't it look like that?
Mm-hmm.
So just think of this secant right here and think of the slope of that secant. Mean value theorem says this: as long as your function's continuous, all right, as long as it's differentiable and continuous, there's no crazy corners, no breaks, no jumps, but it's nice and smooth like a polynomial, then the mean value theorem states somewhere between x equal to 1 and x equal to 5, there's got to be a point on your curve where the slope of the tangent line of the curve has to be parallel to that secant line.
Gotcha.
This is the mean value theorem. So we'll take this part, we'll make the exact graph, but that's the concept of mean value theorem. You know what's going on? All right, let's say this was x equal to 5. Oh, there it is. And this is x equal to 1 right there.
Mm-hmm.
And that's a secant. And you and I know how to find the slope of a secant. We don't even need calculus. We just do rise over run, true?
Mm-hmm.
Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. All right. As long as this curve is differentiable and continuous on this interval from 1 to 5, then somewhere along the route, somewhere between 1 and 5, and it could happen more than once, but it has to happen at least once. It has to happen at least once. There'll be a point between them where the slope of the tangent line is parallel.
So they both are the same m.
That's exactly right. That would mean they both have the same slopes. So somewhere, when I want to make a line that's parallel to this, it looks decent. And you're like, okay, there's my tangent line. That looks better. There's my tangent. At some point, slope of tangent to curve must equal the slope of the what?
Secant.
Secant.
Mm-hmm.
Now, we can write out this theorem, we can apply this problem, we'll look for that point. I say we find the point. It'll be a point between 1 and 5,
Mm-hmm.
okay? It's gotta happen. It's gotta be at some point between 1 and 5. Maybe it's at x equal 3. But maybe it's equal to x equal to 3.5 or something. True? Maybe it's exactly halfway. Sometimes it's exactly dead center in the middle where it happens. But it has to happen at least once, and it can happen more than once. It can happen more than once. Okay? So, I think we should write out the mean variable theorem. Well, the beginning part says this. If your function's differentiable and continuous on a to b, then what has to be equal? Let's start with slope of secant. What would be slope of secant? What's the formula for that? Remember, no calculus. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1? Well, if I call this a and I call this b, I guess I could write that as
F of
f of b minus
F of a.
f of a all over
B minus a.
b minus a. Alright? So we're saying, alright, that slope must be equal to the slope of the tangent
Of the
drawn
del
to the curve. And this is going to be real easy to write.
F prime of B minus F prime of A.
Even better, do you agree? How about just f prime?
Yeah, F prime, sorry.
Does that work? But I'm with you. we're like f prime, and we're like, at some point, there's gotta be some, so we gotta make up a letter. Let's choose a letter other than A and B. At some letter other than A and B, there's gotta be a point between these two right here. 5, B at some point along the way, maybe at 4, maybe at 3, 3.5. At some value between x equal to 1 and x equal to 5, or x equal to A and x equal to B. So you wanna use a little C word?
Yep.
So we'll use C. The author does the same thing. Alright, here's A, here's B, some point C. But we gotta say C has to be what? Between which letters?
B and A.
There we go. Alright, very good.
Okay.
And you'll see it, where is this written? Somewhere on here? Do you see it? I got it buried near the bottom though. I want to go way near the bottom of that sheet. So that's what I mean. You want a summary of 4.1 to 4.3? You got it right there. This will hit on everything. It's just all piled into one sheet. So let's try this, someone. You go, what's the question? Can you find the value of C that's between x equal to 1 and x equal to 5? Such that the slope of the secant between 1 and 5 is equal to the slope of the tangent. Let's try that. What would your author say? I know a number. Now look, he has to say numbers because could there be more than one?
Number.
This one I think you're going to find only one, but there could be more than one, right? Think of curves like sine curves. Or some of the things that go like this. And if you did a tangent, there might be a few places where it's like, right? We could draw some of those. Number 7, I put number 7 for practice. So if anybody has questions on number 7, let me know. I might even put it on the board after we do this problem. All right, final number C. That's satisfied. The mean value theorem. I went for mean value theorem, I'm just going to put MVT, okay? Mean value.
Is this called the Rolle's theorem?
Oh, you're good. That's coming up.
Okay.
Rolle's, it's going to be very specific. You'll like that.
Yes.
But if you understand mean value theorem, Rolle's theorem, you're going to be like, piece of cake. You're going to like Rolle's theorem. This is mean value theorem, right? Between A and B, there's got to be some C value where the slope of this tangent equals the slope of the secant. Well, in this problem, we're going to find that number C. All number C, it's satisfied the conclusion of mean value. On the interval, what was the interval?
1 and 5.
And I'll just point like this. On the interval 1 to 5. So I say we start with the easy part. What's the easy part?
Slope of the secant.
Yeah, let's do slope of secant. No calculus, right? Right? F of 5 minus f of 1 all over 5 minus 1. Okay, what's f of 5? This is, y sub 2 minus y sub 1. This is also, by the way, do you remember this? Average rate of change of the function. Remember that from day 1?
Mhm.
That's really what we're doing. This is called average rate of change of the function on the interval 1 to 5. We don't need derivatives, this is what's fine, but it's also slope of the secant curve. All right.
So f of 5 is
What is f of 5? And by the way, as we're doing this, you want
negative,
to help me out? Maybe we should make a decent curve. I got
negative,
this image.
negative 30.
F of 5 is negative 30?
Yeah, so 5 squared is 20. Sorry, no, that's 5 squared, sorry. 25 times
Yeah,
3 is
5
7.
minus 60
Plus 7.
5 minus
plus
20.
75. Is that 20?
Yep.
20. Minus throwing, by the way, the curve. You're going to help me build it. Like I said, 1, 2, 3, 4, 5. It got all the way up to what? Way up here. Woo! We knew that's parabola. All right, what's f of 1?
F of 1.
Negative 4? So 20 minus negative 4. curve doing what? Right?
Mhm.
I think it's pretty steep. I think it's pretty steep, but that is a curve, everyone. Let me give it a little bend to it. Going up. Now, slope of secant. You just gonna get the slope of that. Whoa, yellow. What's the slope of this secant? We're finding it right now.
6.
6. So in this straight line, you agree it rises 6 notches for every one notch it runs to the right? Okay. Then put an equal sign, and f prime of x on this side. Wait, I thought we're supposed to put c. You can put c. If I'm saying let's just do f prime of x, and at the end we can make it a c. Does that sound good? We're gonna make it c, okay. Then you gotta write it in terms of c, but what's the derivative of that?
Negative 12 plus 6x.
Good job. Derivative of 5 is 0, right? Derivative of negative 12x, negative 12. Derivative of 3x squared, 6x. Right. No chain rule needed, no quotient rule. Nice and simple, huh? But how do you solve this equation?
That equals to 6. The derivative.
6 equals negative 12. Whoops, get that x off there. Where'd that go? 6 equals negative 12 plus 6x. Now, how do I get that off that side? What's 6 plus 12?
18.
18 equals 6x?
Hmm.
What's x equal to?
3.
And I'm laughing because isn't that dead center between the what?
1 and 5.
You know? You're like, is that always going to happen? It doesn't always happen that way, but it's like smack dab right between a 1 and a 5, right at the 3. And when there's x equal to 3, I'm going to put right there on the curve at x equal to 3, I'm going to draw a tangent line. This tangent line should be what? Totally parallel. I'll do my best to make it look like it's parallel. See how their slopes are equal?
Mhm.
But it did happen right between 1 and 3. And sometimes you'll find that. If they went from 0 to 6, you're like, watch it happen at 3. Right? If they went from, what? I'm thinking 7 to 9, you're like, it might occur at x equal to 8. But sometimes it's a fraction. But it has to happen at least what? Once, and it can happen more than once. So I'm going to draw, this is number 7. I'm just going to draw a curve, and I want you to see, if we take the endpoints, how many times you can look at this image and tell me how many times you can tell the slope of the secant would equal the slope of the tangent. Okay? First of all, do you have any questions on this? Cool. I'm going to come back to this, and I'm going to change this, because Art asked about something called Rolle's theorem. It's just slightly different. We're going to take this and add a couple elements to it, okay? This is number 7. All right. Let me do my best to draw this. Okay. That's good. All right, endpoint, and when this is your A, and that's your B. This is just some other curve, right? And it's number 7. It's actually on the next page, 289. Now, draw a secant between these endpoints. Here it is. Isn't this the secant? Secant. Could you tell me, or just ask me, how many times you could get slopes of tangents that would equal those slopes of the secants? Basically, how many tangents along that curve are parallel to that secant? Who sees one? I'll just start drawing them. There's more than one.
2.
Where do you see one? I'll put it.
On the first one.
He said on the first time. He said right around here when there's some spot. How about right there? Is that the only one?
There's 3.
Where's the next one? Is there one in here?
Underneath.
Probably about right there. Remember, tangents hit that curve in one spot. And it's
And
the parallel, is that it?
then the left.
Or about there. So how many?
3.
So that's what I mean, it can happen more than once. It can happen more than once. A lot of times you just get once. Cool? Neat, as long as it's differentiable and it's continuous, right? Crazy thing, you got holes and stuff, no, this game's over. Doesn't automatically have to happen. All right. Now, let me come up with a number. I think I'll use 3. Let's see. 5 minus 12x, 3x squared. Just make sure. 3. I apologize, I should have checked that problem a little bit more carefully. These were right. Guess where the vertex is of this? It's actually a little bit lower in here. So anyways, this graph actually would have done what? Remember negative b over 2a?
Uh-huh.
So when at 2 it got to its lowest point.
But negative b is positive, right? So that's positive x, 12 over 3.
So what's
So
going on at
4.
x equal to 2? X equal to 2, you get 12 plus 5, 17 minus 24, what's that, negative 7?
Uh-huh.
So when at x equal to 2, we got a little bit lower at negative 7. But you know what's neat? What goes on at x equal to 3? We got these right, Owen. This was the point 5 comma 20. This was the point 1 comma negative 4. At 2 it actually reached its vertex, so it was like, yeah. But then at 3 it gets where?
No, vertex should be at 4.
At 3 it's what?
3 is 6. It's going to be 6, right? The same as
Try it out. Let's see. Now, what's going on at x equal to 3 for that function?
5 minus 36 plus
5 minus 36
plus 45.
plus 3 times 3 squared is 27.
27, yeah.
What do y'all get?
30, negative 4.
Okay, so, and when you notice at x equal to 3 it's at what?
Negative 4.
Negative 4?
Uh-huh.
Okay. So at 1 it was negative 4. At 2 it got down to what? Negative 7. Then 3 it got back to what? Negative 4. So this graph's really going like this, and then it got up to this, like that. And we found out the answer was x equal to what? 3. Boop. Right there. Does that look parallel to that?
Uh-huh.
Okay. Cool. Now I'm going to change this image, and I'm going to change the question. Ready? So in your notes, make this a 3. Now, I'm not doing like number 1.
Doing number
I'm
1.
doing number 1.
Okay.
Right? I just want to really see this picture. Okay. 1, 2, 3. We're zooming in now, everyone. 4, 5, 6, 7. At 1 it got to negative 4, right? At 2 it got down to negative 7.
Mm-hmm.
And then at 3, because that's the interval, it got back to what value? Negative 4.
4. Yeah.
Alright. Here's the curve. But you know what's interesting about this question? We just did mean-reality theorem, true? What's interesting about this problem, I want you to apply the mean-value theorem here. And think about the slope of the secant. Look at the slope of the secant. That'd be the slope between the 2 points right there.
1 and 3, yeah.
They're both at negative 4, right? Right there and right there. That would be the secant, right?
Uh-huh.
Alright, here's my secant. Yep, this was done on purpose. So you can say, what's the slope of that thing?
0.
0.
0. Everyone agree? slope of the secant. Why is the slope of the secant 0? Because f of 1, right, takes on the same y value as f of 3. Does everyone agree?
Mm-hmm.
But according to the mean value theorem, it still holds. There's got to be a point between x equal to 1 and x equal to 3 such that the slope of the what? The tangent will be equal to the slope of the secant. And I bet you know where it's going to happen. At 2. And what would be that slope? 0, right? You can see it, true? Yeah, okay, that's just an extension of what theorem? Mean value theorem? Yeah. But there's actually a name to it, and it's Rolle's theorem. Alright, so what's Rolle's theorem? It starts out like this. You can see it with this problem. Rolle's theorem starts out, you know what? What if f of a equals f of b? Right? And then we use all the same language as the mean value theorem. Same language. What if f of a actually equals f of b? As we could see.
Mm-hmm.
And we use all the same language. Well, we can actually write this a little better, can't we? Because we could say this. Right? F of b minus f of a over b minus a, right?
Mm-hmm.
What would all that equal?
F prime of C.
Okay. We're going to improve this. What's f prime of c going to have to equal every time?
0.
Because if these two numbers are the same numbers, everyone, look, you're the same as this guy. You're the same. It's almost like I call it f of b minus f. They're the same numbers. This number here will turn into what? 0.
0.
So we can actually make this Rolle's theorem and say, okay, you're always going to be 0. And there's going to be some what? There'll be some c value that's between a and b. And it's going to have to take a slope of what on? 0. But we can only say 0 here as long as what? If f of a equal f of b. But when you agree, you're like, oh yeah, that's just the mean value theorem. True? Hey, yeah, I get it. You get it, yeah. If those two y values are the same, then the slope of the secant will be 0. And then f prime of c would be 0. C would have somewhere between it, it's got to take on that slope of 0. And it has to happen at least once, right? So now think of the sine curve, right? What if they had a sine curve that went like this? And they said, okay, go from here all the way to here, right? And see how these take on the same y values?
Mm-hmm.
You're like, all right, how many times is the slope 0? You're like, here, 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 here. Do you all agree?
Mm-hmm.
How many times is the slope of the secant equal to the slope of the tangent? You're like a bunch of times. True? So we can have more of those. But we have to work out that math. We were just showing that there's going to be some value. But I think you all know, where's it going to occur? If it was from 1 to 3, it'll occur
Between 1 and
x
3.
equal 2. Let's
Yep.
just make sure. So, I'll keep my 0 here. And what's the first derivative?
Negative 12
12 plus 6.
6 x.
You could put c in here. It's okay if you just leave it what letter? X. If you just don't want to make it a c, and you're solving for x. Well, what value do we get when we solve that? C equals 2. It's nice to see it. Everyone see it? It's just nice to see it. You're like, oh yeah, it's right between them. Rolle's theorem. Cool. Even when I like to put this on a test, I actually like to draw the curve with the secant there, just to help you remember. You know, you see this image of like some curve going like this, and you got like a secant just going, and I'm like, all right. And you saw my language before about the, you know, find that c value that satisfies the conclusion of the mean value theorem. And you're like, oh yeah, I know what's going on. I gotta find a point that's between these two where the slope is what?
0.
What up here then? Alright. And we got it. Mean value theorem. Later on, we're gonna do integrals. And there's something called the mean value theorem for integrals. If you want to do the math proof in class, we're going to need that. Alright? We actually have to use that to prove the mean value theorem for antiderivatives, for what we call an integral. We go, what's an integral? We haven't gotten to that yet. But that's a cool theorem. All right. Let's see what we got here. How about that? Knowing your notes, you can just put 4 points right. Let's tear this function up. Let's start talking about words like where the function's increasing, and where's the function decreasing, and where the function's concave up, and where the function's concave down. All these new terms. Define concavity, right? Make sure everyone understands this whole thing. All right. And we'll work through that problem. Okay, well before we do, let's just look at some things. Everyone a function. Maybe something just goes like that. Where is this function increasing?
Where between it,
Slope is positive.
Over here on this side, right? Where the slope of the tangent line is positive, right? Where was this function decreasing? Over here, right? Where the slope of the tangent was negative. So, isn't the slope of tangent line first derivative? Okay, so I guess this is all we have to do. If we get the first derivative, whenever the first derivative is positive, the function should be increasing. Do you agree?
so should there be a set of value?
What's that?
Should there be limited set of values like between?
That's right, we'll have to find them.
Okay.
We will find them, that's very good. And it's gonna be based off those max and mins, those critical points we find.
Gotcha.
All right, you got it. But at least we know that. We're like, okay, we understand that when that first derivative is positive, we know for a fact that that function is gonna be what? Increasing. And when the first derivative is negative, that function has to be doing what?
Decreasing.
Decreasing. So far, so good? And he goes, but there might seem limit values to see where this happens, yeah? And we will do it through these what? Critical points. We'll get the critical points first, and then we'll start looking at this stuff. We might have to test some points, though, just to see, and when we're saying the words positive and negative, the only way you and I are going to be able to tell if the function's positive or negative is just pick some numbers to plug in there to see if it's what? Positive or negative. We won't be so concerned about the number itself, okay? But we'll see that as we work through a problem like this. All right, so that's what? Increase and decreasing. True? And we'll be able to find those max and mins again. Remember, we find max and mins by taking the first derivative, setting it equal to what? 0. Solve for x. And those are called the critical points. True? But now, I didn't put some limited what? Let me get this thing off here. I didn't put some limited numbers there. So we're going to look at these relative max and mins. Sound good? Now there's another word that's going to come up. It's called concavity. So, a graph that is concave up, everyone, will be a function that does something like that. Hey, doesn't that look like a cup?
Mm-hmm.
So I, on purpose, misspelled concave up. I spelled it what? Cup. Or you can do C what? UP. Cup. Okay, like a cup. So when the graph's doing something like this, it's going to be what? Concave up. Don't worry, we didn't define it yet, but we will. You can't just say that. Okay, just, we got to put a definition to this. But hey, what if the function's doing something like this?
Concave down.
Yep, concave down. Okay, come on, we got to define this. That's not good enough. It's pretty good though. Like a cup, concave up, right? Concave down like an upside down frown. True? Here. Concave down like an upside down frown, concave up like a cup. We'll remember that, true?
Mm-hmm.
Any function, that's where we can go, oh, that thing's for concave up, where's concave down, we can look and find it. But what's the definition? It has to do with the slope. So, everyone, if the slope is always increasing on a certain interval, the function is concave up. Yep, so let's look at this. Let's just make up some numbers. Is that okay? All right, let's go on. We're gonna just make up some slopes. They don't have to be perfect. What would be the slope of this line right here? Let's just make. How about m equals -2? Will that work, everyone? Remember, m is f prime. You all agree?
Mm-hmm.
All right, here's some function, but the slope of the tangent line right there is -2. It's kind of steep. Now, right here, I moved a little bit further.
the slope's not as steep, but it's still negative, do you agree?
Mm-hmm.
Okay, so the slope is -1, will that work? Like, well, it's not as steep, I'm making these up, but yeah, it's like, okay, it's not as steep as that. It's like -1, and that's F prime, right? But do you agree as it went from here to here, didn't the slope actually increase?
Increase, yeah.
-2 to -1 means it got higher, right?
Mm-hmm.
It increased, okay. And then what's the slope right there? I bet you all know.
0.
So F prime would equal 0. And let's just pick above, how about right there? What's F prime right there?
1.
1. And then way up here where it's getting steep, we can just say, all right, maybe slope got up to like a 2. But over this entire interval here of this cup, we said the slope of the tangent line kept increasing. Notice we didn't say the word positive or negative though. That's the definition of concave up. A function is concave up, all right? As long as the slope of the tangent line drawn in the curve is increasing along that arrow. If the first derivative is increasing. We put that into words, it sounds all complicated, and when I think images tell the story. So that's what I mean, like, if you're like, I'm not gonna confuse this. I can just draw a cup, maybe do this, along my cup, and I understand what concave up means, right? Function's concave up. What's concave down mean? It means the slope is always doing what?
Decreasing.
So I'm gonna make up some slopes, okay? M is -2, M is -1, M is 0 here, maybe over here, M is 1. Oh, let me get these right, sorry about that. Everyone's like, what are you doing? 2, 1, 0. Now the slope would be what?
Negative.
Negative.
1.
And then right here. And remember, these are first derivatives. First derivative at that location. First derivative. First derivative. M for slope, first derivative. What happened with these slopes? They kept decreasing when it was concave down. Cool? So you could always define it if you want. You're like, okay, I know what it means. For a function to be concave down, that means the first derivative is always, I don't say positive or negative, I say the first derivative is always decreasing. But the summary of all this is really these images. It's really these images. Upside down frown and the concave up. Go ahead, Josephine.
Do you always take it from left to right?
Yep, very good. We always read graphs from left to right. We always describe graphs from left to right. Outstanding. Because if we didn't do that, we could get totally flip-flop answers. Very good. Everything in mathematics, we describe left to right, we write intervals from left to right. Or if you want, you could say we do everything from lowest to highest. And then you got range taken care of. Okay? Very good. Hey, so I'm going to draw an image. I wonder if you all could tell me where it went concave up, where it went concave down. Can I erase these? Yeah, there we go. Get some graph. I just want to make some kind of function like that. All right. What's it doing right here? Very good, it's decreasing. Is it concave up or concave down? So you got to think of the cup. Ooh, good, it's like the cup part. So I'll just put a CU right here, right? It's like concave up, isn't it? Now somewhere around what? See, I see in here, I see it's concave down. So somewhere between here and then here, it turned into what? Concave down. It probably occurred what? Perhaps maybe halfway between this and this? We don't know precisely right now.
On the left
We
side,
can
how
do
do you,
that.
how do you get the that's decreasing, right? Concave up. On that side is this.
That's right. And so a function can be concave up, but the first derivative could be negative. That's it. Because remember, the whole idea of concave up means the slope of the tangent line or the first derivative is always increasing.
So is this the first derivative, the function that you drew?
Oh, good question, Art. This would be f.
Okay.
So if this was f, everyone, this function that I drew, this is f. We could say f is concave up from about here to here, and then stop. And then right about here, it turned into what?
Concave down.
Concave down, just about, roughly. You go, wait, how do we find that point exactly? That's what we're going to talk about. We'll precisely find that value, true? And then right about here, concave down, and then after here, it went back to what?
Concave up.
So it looks like this function here was concave up from about here to here, then it went concave down, then it changed to what? Concave up. So there's got to be a name for a point where a function changes concavity. And there's a name for it. And it's called a point of inflection. So how many points of inflection do you see?
1, 2, 3.
There's two of them, aren't there?
Yeah.
Now if you want to write POI for point of inflection. So definition of a point of inflection? A point of inflection is a point such that the function changes what?
Concavity.
That's the definition. You can call it a POI, a POI. I have some students who go, no, even better, I'll call it IP for inflection point. So what do you prefer? Because you'll probably label these things when you're doing your math. You want to call them POIs, point of inflection, or do you want to call them IP, inflection points? Your call. I call them POIs. I got a couple POIs here, huh? Where the graph changed concavity. True? So let's do a couple problems where we just blast it out from start to finish, and we find everything like this. See this graph function I got here? Let's find where that function's increasing and decreasing. Let's find where that function's concave up and where that function's concave down. Let's find all the points of inflection, all the points, if there are any. Because you go, does there have to be a point of inflection? No. Everyone, think of the parabola like this. It's always concave up, so it never changes what? Concavity, true? But if you go to x cubed, I think you'll find 1 point of inflection on x cubed.
0.
I want to see if everyone, oh gosh. What do y'all think? X cubed does the what? The snake.
Mm-hmm.
Can anybody see the 1 point of inflection on that graph?
0.
Oh look, concave down, stop. And right there it changed to what? A concave up. So right there when you got a little point of that function, point of inflection. But some functions don't have points of inflection, do they?
You know,
You think of y equals x squared?
most likely in sine and cosine function, that's where you have more.
Oh yeah. My goodness, sine and cosine functions, they're always changing what? Concave up, concave down, concave up, right? Someone good with this stuff? Yeah? So, you ready to blast through this thing?
Yep.
Alright. We should make a big list. Where's f increasing? So we're gonna have to list the interval. Where's f decreasing? Alright. Let's find local max. At x equal to blank, local max is blank. At x equal to blank, local min is blank. Now in here we're going to put integrals. Where is f increasing? Notice I didn't say f prime increasing. I said where is f increasing, okay?
Uh-huh.
We'll put some intervals down on that. We'll find all this. Now everything I wrote on the board so far. Local max, local mins, everyone, we won't list the critical points, but can we at least discuss it? Maybe in your notes you'll say these are critical points. Okay? All this is done with which derivative? First derivative or second derivative?
First.
First derivative. So would you in your notes? Just make a note. See all the stuff I've written on the board? You go, what's going to determine this? How am I going to find these? You're going to find all these with the first derivative. Cool? All this stuff. So they're like, all right, man, I'm going to get all this stuff with a what?
F prime.
I'm going to use f prime to get this thing. Somehow, some way. Now, under this, let me put some other things. And when I say we list any points of inflection, can I just put poise?
Mm-hmm.
Point for point of inflection, or feel free to write IP for inflection point. We'll see if we can find any of those. We're going to put the interval where the graph is, the function is concave up. And then we'll list the interval where the function is concave down. But I put a big wall, because you know what we're going to use to find this stuff? Not the first derivative. We're going to find the second derivative. You go, why? Because if you recall the definition of concavity, we said O is where the first derivative was increasing. And it was where the first derivative was decreasing, right? So we're going to look at, not first derivative, the determinist stuff. We're going to look at
Second.
Second derivative. So yeah, let me just go, I'll get this out of the way. And don't worry, I'm gonna do a couple problems like this today. I think one with the graph stuff. So that's what we'll do. But always keep in mind, this junk up here, where's the function degree? Where's the function? Where's the max? Where's the min? First derivative. All right. Oh, where are the point of inflections? Where's the concave up? Where's the concave down? I'm looking at what? Second derivative. Cool. Now, some students in this classroom, they've taken calc before and they're sitting there going, you know, you could actually use second derivative to find max and mins, and they are correct. So we could talk about that later. All right, you can actually use second derivative to help you determine, but you still have to know the critical points. And try, plus, don't you agree, to get the second derivative, you always got to move through which derivative? First derivative. There's no shortcut. You can't get around the first derivative to get the second derivative. So if we're going to do the first derivative anyways, might as well find this stuff out. Sound good? All right, let's start out. Everyone, let's find
For derivative.
they call this the first derivative test. This first derivative test will help us determine all this stuff. Let's use the first derivative test. All right, the first derivative test, I get 3x squared minus 1.
3.
Now, what should I do with this in the first derivative test? I should set this equal to something.
0.
Brilliant. So that's what we're going to do. With the first derivative test, let's always take the first derivative and set it equal to 0 and determine where it equals 0. And I'll put whisper, parentheses, or where it does not exist. So if you got some crazy word function, you know, with a fraction and there's an x in the denominator, you can also determine where it doesn't exist. Because sometimes max and mins could occur there, but that's not every case. This is a simple polynomial. So I'll set this equal to 0, and our factoring skills come into play. How are you with factoring?
The 3.
All right, I heard it. Dora says you can factor out of what?
3.
3. Now what am I left?
1.
That's called a difference of perfect squares. How do you factor a difference of perfect squares?
X.
X minus 1 and
X plus 1.
x plus 1. I think today, every function we're going to deal with, at least today, you'll be able to factor. You won't have any trouble factoring. But you could say the more complicated ones, maybe I have to do quadratic formula or something like that. But yeah, pretty simple so far. Now, yeah, you sure can. Josephine, very good. Be careful when that word critical points. I don't see 3 critical points. I only see 2. Sometimes students mistakenly think, is that a critical point? No, that's nothing. Let that 3 hang there. Your critical points are points such that x, right? First derivative equals at certain x values. So it looks like we're getting how many critical points?
2.
2. One of them's where? And the other one? Now I do want to say something about critical points. Sometimes a critical point actually could be a point of inflection. You never know until you keep working it out. So critical points definitely find your max and mins. They definitely do. But sometimes, I didn't want you to think if you had like 5 critical points, that you're like, okay, these 5 critical points, they all got to be max and mins. You know, one of them might be the point of inflection or something. We'll find out as we keep working through the math, okay? Now, what do I do next? I know at x equal to 1, x equal to 9. This is called the first derivative test if you wanted to write that down, what we're going to apply. After I find these critical points, I want everyone in here to make a number line. You might say, shouldn't I draw the curve? We all have knowledge of x cubed graphs. What do they look like? That's not a bad idea if you explore this picture, clearer beforehand, but sometimes the function's so crazy, we don't have a sense of what the image really looks like, But this always works. Make a number line. And on your number line, put your critical points. So make sure, hey, Josephine, I have to do this from lowest to highest. So which one of these is lower?
-1.
So I'm putting -1 to the left and 1 to the right because it is a number line. There's my critical points, true? We're trying to find these numbers, if there are any, and these numbers. All right, now, let's go back to this definition. We said a function is increasing as long as its first derivative is what?
Positive.
Positive. So that's what we're going to do. This is f prime, right there, equal to 0. This was f prime, equal to 0. So I want you to think, you and I are going to plug some points, some test points. But I have to be so very careful, and you have to be so very careful when we pick test points, we plug it into the right thing. This is called what test? The first derivative test? then I'm gonna pick some test points in these intervals, and I'm plugging them into the first derivative, okay? And if the first derivative is positive, the function's increasing. If the first derivative is negative, the function's what? Decreasing. So, look, I'm gonna put an f prime here. Maybe I'll rewrite what f prime was so I don't forget. What was f prime? It was 3 times a what? Which one do you think is gonna be the easiest to plug numbers in? I think this one. It's up to you. You might say that one, but I like that one. It doesn't matter. I'm just gonna write it again, and I'm gonna put a box around this. Because I wanna make sure I'm putting my test points into what? The right thing. This is called the first derivative test. And it's gonna give us all those answers there. Now, who's got an easy test point between -1 and 1? 0. Where do I plug it? You plug it in the no, don't plug in the original. Plug it into the what? First derivative. I don't care about the number, I care about the sign.
Sorry, yeah.
Is it positive or negative? It's negative. Now I don't want to rush you on. This is you plugging this stuff in. You might have plugged it in here, you might have found it easier. 3 times 0 minus 3. Yep, use your calculators if you have to. Let it go, let me just see. 3 times 0 minus 3. Is that positive or negative? Okay. Okay, keep in mind, a lot of times these alternate. I can't say it's 100% of the time, but a lot of times if that's minus, you know how graphs behave, they what? Don't they do this? They do this little wave thing. So if it was decrease, it's probably going to what next? Increase. But every once in a while you get a goofy function that does like a minus, then the minus around a critical point. So just be careful.
Can you plug numbers into the original f prime?
No.
Like the 3x squared minus 3?
You sure can. I wrote it this way. Look, let's say you preferred that. That is totally fine. I want you, Josephine, or any student in here, to pick the one you find the easiest. What you find the easiest to plug into. If you're doing it mentally or if you're using a calculator. Okay? Just make sure you don't plug it into the original function. Is there ever going to be a time we plug something in the original function? Oh yeah. You'll see. In this list of them, there's some blanks in there. We're going to plug some numbers in the original. So we got to know that. That's the thing about Cal. You go, wait, oh, I plug in here. I plug in there. These are going in here. Now, who's got a number high on 1?
2.
All right. I'll use yours, Josephine. 3 times 2 squared minus 3. Positive or negative?
Positive.
It's positive. Now I need a number over here. Negative 2?
Negative 2.
3 times negative 2 squared, which is positive, right? 12 minus 3. Cool. I like this one, but that doesn't mean every student likes this one to plug numbers in. You find the one that's the easiest, right? Whether it's the original or after you factored it. Just like we thought, everyone, didn't these signs keep alternating? Yeah, so expect that. Expect that. If you find one, you should see it, but I would double check a few of them. Don't assume they always went plus, minus, plus, minus, plus. Right? Now, look how many answers we got. First of all, I think with a pencil, could you just make a rough graph of what's going on here? Doesn't have to be perfect. If a function's got a positive slope, what would it do? So do it. Take your pen, like right underneath, I don't care how sloppy it is. Josephine, I don't care how sloppy it is. Just take your pencil right here and go, okay, the function was kind of going up here. And this is f. I'm driving it, I'm drawing a rough sketch of f here, right? All right, f went up. Then what happened from here?
Went down.
Oh, it went down. Now what happened to 1?
Going up.
Now I'm drawing f, so I do want to point out, I know I got an f prime right there, but let me just put this as f. We know what to do now. Where is the function increasing? What intervals? Where are the pluses? Negative infinity to the
Negative 1.
negative 1. Is that the only part though?
No. Then
I'm looking at these pluses, right? Where else?
then union 1 to infinity.
Everyone agree? Arjun, I'm just looking where I got my little pluses, right? That means the function was what? Going up. So I got to put a union and then put 1 to infinity. This is to make sure you communicate this way. This is interval notation. You can keep all open parentheses. Don't worry about any closed brackets. And what do you do if you got more than one interval? Just put a union symbol. I don't think we're going to have a union symbol here, though. What do you get there?
Just one, negative 1 to 1.
Looks like a point, but keep in mind, I'm going to put this word in front of it, and that's an interval. I didn't want you to think that's an XY coordinate. That's an interval. Does this make sense?
Mm-hmm.
I know you go, well, that's a simple function. But hey, if you can do it with this one, you can do it with them all. Now, I think we got this stuff. Everyone, look, which one of these is a local max? Which one's a local min?
So negative 1 is the local
You can see
max.
And you did this for me. You were like, so you might do that to see which one's a local max. Absolutely, a local max is when the function goes from what? Increasing to decreasing. Some students though, I get a kick out of this, and I don't get mad at them, they memorize. They go, okay, I'm gonna memorize this. When I see plus to a minus in my f prime, that's a max. I mean, you could do that. I think it's more of what? Conceptual? You're like, oh yeah, it went up, and then it went what? Down. But yeah, students will do that. They'll show me their notes, and they go, look, professor, this is what I got. They're like, they get any point, figure it's plus to a minus on an f prime like this. I know between a plus and minus, they go, this has to be a max on an f prime. And that's true, but that's what they'll memorize. I think it's more if you just make it conceptual in terms I understand it would increase and then decrease. So what's this number?
1.
There's a local max at -1. Cool. Now, where's the local min?
0.
Is it
No,
0? Oh.
no, 1.
Yeah, very good. Look, anyone see this? The function will what? There you go. Local min right there. So you got a local min right here. You got a local max right there. True? So I'll put this.
Does it always correspond with critical point?
Yep. But hey, Josephine, let me be careful. Sometimes you might get 3 or 4 critical points. It doesn't mean all 3 or 4 you have to fill out all your local maximums. One of those may be a point of inflection. Okay? Maybe or may not be. I just want to point that out. But the absolute essential test for points of inflection, Josephine, has to be through second derivative. But I just want to make you aware that sometimes a critical point is one of your points of inflection.
It's also when
You know?
solving for zero.
That's right. That's right. Now, everyone, this is interesting. So far, so good? Are you sure everyone okay with this?
Mhm.
All right, here we go. I've been plugging everything into what so far?
First derivative.
Look at these blank spaces. In the wording I have here, I'm saying how there was a local max of the function. At x equal to -1, there's a local max of the function, and then I said the word is. If I'm talking about I'm talking about the y value of the original function. Guess where I gotta plug these now to fill in these?
Original function.
I'm going to the original. Alright, so I know everyone that's where sometimes this stuff can get confused. You're like, what the heck's going on? He was just plugging things in here. But if I'm putting this where it is, and I'm talking about the actual max of the actual function, I'm putting it all the way back in, way up here, right? Way up there. That's to get these. Does that make sense? So let me just see. What's -1 cubed minus 3?
2.
-1
I get
plus
negative.
3. 2 is 2.
-1 plus 3, 2?
Yeah, so
Good
negative
job,
1
everyone.
plus.
I apologize, that's right. Now I want you to plug a 1 in here.
Local min.
Plug in the original. By the way, if you accidentally plugged it in here, I'll tell you what you'll get every time, zeros. Does that make sense? If you accidentally plugged it in here, you're getting slope of 0. Right? But it goes to the original. So this point right here was the point what? Oh, that was -1, 2. What was this point?
2, 6.
We got a great sense of this graph right now, everyone. At -1, it got up to what? 2, and then over at 1, it got down to what? What was it going at 1? It got down to what? -2, this is one of those snakes, right? Anybody know how to get a y-intercept in math? Just set x equal to 0. What's 0 minus 0? Why do we need a pre-calc class? Think about it. Remember when you had to build graphs in pre-calc? They talked about multiplicity and all this stuff? You're like, man, I can just do this stuff. That's a nice pretty graph, isn't it? Cool. Hey, let's keep going though. By the way, as you look at this image, you might already sense if there's any points of inflection. You see any concavity changing in there?
Yeah.
Can anybody, raise your hand, can you predict how many points of inflection we'll have? Just look. Look for between the cup and the upside down frown. How many do you see, Ben?
1.
Brilliant. And when he's saying there's only one. Because I see, look, upside down frown. And then over here I see the what? Concave up. Right? And somewhere, and we do it left to right, Josephine. So somewhere between the what? The upside down frown and the cup. It looks like there's a point of inflection. Where do you think it's happening? Where do you sense that probably there's a point of inflection?
At the x-axis.
Doesn't it look like it?
Mhm.
Y'all agree that's where it changed from the concave down to the concave up? Halfway between this max and min location, right? I think we're gonna be right, but what's the absolute test? This what? second derivative stuff. So I'm about to erase this. You okay with that? All right, it's getting wiped out, except for one thing. That thing. Are you sure? Don't need the cell phone in? You got it. Now, what are we doing to get these answers? Second derivative test. All right, so what's the second derivative? You know what we said it equal to? 0 already? Oh, dude, or doesn't make sense. That comes up. Okay. So second derivative equals 0, and you solve for what? X. Now, if 6x equals 0, I'll divide a 6 on both sides. What's 0 divided 6? 0. Now, let me tell you what this is. Be careful with this. Sometimes students make little mistakes. You know what? They think, oh, here's what they go. Oh, a second derivative is where the a point of inflection is where the second derivative equals 0. Not exactly. This is called a possible point of inflection. We'll define it. What word do I have up there? Possible. I didn't want you to think, everyone, every time you just set second derivative equal to 0 and you get numbers, that they're points of inflections. They're all possible points of inflection. So what's the true definition of point of inflection? We'll go back to what we said earlier. It's where the second derivative does equal 0, but also it's where the concavity must change. Do you hear me? So there's only one way to make sure the concavity changes here. Right now it's just a possible point of inflection. We got to make another number line. And we're not going to call this the first derivative test. We're going to call this the what?
Second
The
derivative.
second derivative test. Okay? That sound good? We can call it the second derivative test for concavity. How about that? Yeah. How about that? The second derivative test for concavity.
Wait, so does the second derivative always equal 0 for the point of inflection?
No.
Well, it will have to equal 0, but something else has to happen. That's true, but there's something else. The concavity must change. Okay? So what I'm saying is, let's say you and I, Josephine, we found 3 values where the second derivative equals 0. Maybe not all 3 are points of inflection. We have to go to this number line here, and we got to analyze it to make sure concavity changes. Okay? Cool. So, everyone, I want you to list all your points of inflection on this number line. How many were there?
Just
Possible points of inflection. All right, here it is. You go, why can't we call these critical points? That term's already been taken. That's where the first term equals 0. So we call these not points of inflection, but what? Possible points of inflection. Now I'm going to bracket this off. And when I like to rewrite the equation, this time Josephine only got one option, just 6x, right? All right. Now I need some test points. What's an easy
1.
test point over here? 1?
Yeah.
All right, 6 times 1, I don't care about the number, Sarah. Just, is it positive or negative?
Positive.
Positive. And then, what's the test point over here? How about
Negative.
-1? All right, I don't care about the number.
Mm.
Positive or negative, I plug a -1 in there. It's what?
Negative.
Negative. Now, since it's second derivative, let me go back to this. Remember these images?
Mm-hmm.
Well, what's going to help us know about this stuff? This is concave up. F is concave up. And on a graph like this, F is what?
Concave down.
Concave down. Feel free to write CU and CD to abbreviate.
Mm-hmm.
Something interesting going on with second derivative. The second derivative will be
Increasing.
negative.
Negative. Sorry.
Oh, excuse me, on this, positive.
Uh-huh.
Over here, second derivative will be
Negative.
negative. Second derivative will be positive when it's concave up. Second derivative will be negative when it's concave down.
Yeah.
Always. So I always want you to think with this thing, Josephine, that's the concave up, you know second derivative must be what? Positive. And you go, why? Why is it positive? Because the slope of the tangent line to the curve is always increasing. If that makes sense.
You just said it. Follow my table.
Yeah, exactly. So, everyone, where's the concave up?
So concave is when it's positive. So that's
0
0
to-
to infinity.
All right, where was it concave down?
Negative infinity to 0.
Then what if you want to make little images in here? You can make like a cup like this. And then here you can make a little what? Upside down frown if you want. But that's what's probably going on with the graph, you see it? Josephine, did it change concavity?
Yes.
What I mean is the signs would have to change. So is that a point of inflection?
Mm-hmm.
Now, hey, think about this. What if it went minus minus? That would not be a point of inflection. You follow me? Does that make sense?
Mm-hmm.
You bet, everyone. If this thing went, look, minus minus. Now, students in here might go, can you show me an example? I'll be glad to. A real simple one, too. But it's a point of inflection because it changed from negative to positive. It changed from concave down to concave up. F is concave up. And then when I'm saying this, I have to be careful with my wording. I know I abbreviate up here. I'm saying F is concave up and F is concave down, but we use second derivative to find these answers. Now, for this, can we just say this? X equal to 0. If you used Weber sign, you would have to put the y value with it like an xy coordinate. Everyone, I'm okay if you just list the x values for points of inflection. Does that sound good? I'm serious. You just tell me the x values. But if you use Weber sign, it would make you put the x and the what? And the y. Okay? So Art, I'm okay if you just, when it comes to points of inflection, if you just say it occurs at x equal to, and just put the value.
Okay.
Cool? Oh, great job with this. Can we do another? Can
Sure.
we blast through everything? All I can do is erase all these spaces. Look. I'll leave this up here. I'll take that off, that off, that off. Isn't that cool? Look at all the stuff you know about this graph. Make a beautiful graph. You can answer all these questions. Cool? Yeah?
You're doing one more?
You ready?
Yes, sir.
All right, this one's coming up, everyone. Oh, and before I do it, I apologize. I wanted to show you one image. Remember execute? You hit solid what? Hey, who in here thinks it's a good idea maybe even to look at some of these graphs on a calculator before you start? That's up to you. Just get a sense of where maybe you might have a what? Point of inflection? That's why that tool's there to support you, okay? But you'll be able to create everything. I wanted to show you something. X to the 4th. Now, did you know that graph looks just like x squared?
Mm-hmm.
Okay? So watch what would happen. Let's say I'm looking for points of inflection. So I'm going to blast through the first derivative. I don't care about the first derivative. First derivative is 4x cubed, right? This is what I'm concerned about, everyone. What's the second derivative?
12x squared.
All right, check this out. Everyone, solve for x. I'm in the second derivative. Josephine, we were talking about the definition of points of inflection. We said points of inflection, the second derivative must equal 0 at those values. Or lightly in parentheses, I say, or it does not exist. But it doesn't guarantee it's a point of inflection, right? Something else must be true. Second derivative must be equal to 0 or it does not exist. And the concavity must do what? Second derivative must change signs. So, look at this. What's the value? What solves that equation? X equal to what?
0.
So right now, this is not a point of inflection, this is called a what?
Possible.
Possible point of inflection. And you'll notice something, look. My second derivative test? Anyone want to I mean, look at this. What's going on either side?
Both are positive.
It's positive over here. You put a negative in there, it's still what? Are there any points of inflection on that thing? Because this graph looks like what? What's it behave like?
Isn't that the same as x squared?
Yeah! Do you see any points of inflection? That's why, look what's happening. There are no points of inflection. It's always concave what? It's always concave up. Do you follow me? So that's why I wanted to show you that you go, oh, I'm going to make sure just because I get second derivative equal to 0 doesn't guarantee it's a what? Point of inflection.
So,
Right? Does that make sense?
now can I ask you a question? So,
Sure.
Can I conclude from this that if a function is even, so that's going to be concave up, and if a function is odd, that's going to be concave down. But a function that can neither be even or odd, like this one, that could have a point of inflection.
That's pretty good. That's pretty good. And can you, that's pretty darn good. And I'm trying to think of, here's some other neat even functions. How about this guy? I gotta match that, make it even, right? I mean, there's an even function, but do you see a lot of points of inflection in there? You can. All right, look, it's concave what? Concave down, then it went what? Concave up, then it went concave down, then it went concave up, then it went concave down. He's hitting on this even functions and odd functions. That was good, Art.
Thank you.
Very good. All right, here's my next one. Oh, and hey, I know you might need time to write outside. I got it easy. I just get to erase all these. All right. All right. All right. All right. X cube's too small. We gotta do X to the fourth.
Give an odd function. Is that going to, that looks like an even function, right?
Yeah, you're right. That's even.
Yeah, let's leave it, want to do an odd function or something?
We can do an odd on the next one.
Okay.
Yeah. You bet, Art. We should just make one up too.
All right.
Or we can do a sine trig function.
That's fine, yeah.
All right. What test do we have to start with first? What do you get?
4x cubed minus 16x.
What do we set equal to?
0.
That one right now. All those factoring skills are coming into play, right?
Uh-huh.
Josephine, I have to mention, likes to graph the first derivative. And she'll check the x-intercepts, okay? So if you're like, that's so great with factoring, you can use that tool to help support you in that manner. But, Sarah, can I just factor anything out of a 4 and a 16? 4?
X.
4.5.
And the x too, right?
Yeah.
But that, I knew you knew that. You hit the 4, and perfect. What are we left with this time?
X squared minus 16.
X squared minus
With 4 minus 4, sorry.
Oh, good job. That is. Isn't that a difference of perfect squares?
Mhm.
Sometimes you get trinomials, sometimes you get these difference of perfect squares. Worst case, Claire, is when you get, you go, oh, I can't factor, now I gotta do quadratic formula. I know, we're like, sometimes that happens. But you can use your grapher. Josephine, you'll be alright just getting what those numbers are, you know? That happens. Alright, I'm gonna keep factoring. 4x, leave it. X plus 2, x minus 2. How many critical points this time?
3.
3. You go, I thought you said you ignore the 4. We do. We don't really care about what we're talking about, that x there. Yep, Sarah outstanding. She goes, it has an x. I want to be aware of that x out there. So let's see. What makes 4x equal 0?
0.
0. Alright. Critical point. That's a CP. Critical point. What makes x plus 2 equal 0? Some of you don't have to do as much writing as me. That's okay. I just like to show what we're doing. We're finding these critical points are -2. And then what makes x minus 2 equal 0? There are 3 critical points. Alright. I can start filling things in. Not yet. I have to do something called the first derivative test. I make a number line, right?
Mm-hmm.
Alright. You just make a number line. Now list from lowest to highest. What's the lowest number in there?
-2.
It goes back to your point, Josephine. Lowest to highest, left to right. We describe everything from left to right. I gotta do this left to right, numerically. Alright, we got a bunch of test points to plug in here. But it's probably, not guaranteed, but it's probably gonna do what? The signs. They're probably gonna alternate, right?
Mm-hmm.
Everyone agree? Right, we expect that. Cool? They're probably gonna like plus, minus, but we'll see. Doesn't matter where you start. You wanna use -3?
Okay.
Alright, I like this one. So I mean negative
So that's
times a negative
negative, positive.
times a negative. Do you agree?
Yeah. That's
So everyone, if I plug a -2 here, this is the one I like. You might like that one, I like this one. -3, that would be negative. -2 plus 2, that would be negative. -3 in here would be a negative. What's a negative times a negative times a negative?
Negative.
I don't care about the number. I'm just looking at the sign, right? Always remember that. I just care about the sign. All right. Between -2 and 0, an easy one.
-1.
-1 work?
Mm-hmm.
4 times -1, negative.
Negative.
-1 plus 2,
Positive.
positive. Negative 1 minus 2 negative. So listen, what's a negative times a positive times a negative?
Positive.
You all agree? A negative times a positive, you get two negatives. Just like we thought, it's starting to what?
Flipping.
Starting to flip. I mean, can you what do you think this is going to do? I
Negative.
mean, so we're like, it's probably going to do it. I know it's not guaranteed, but it's probably going to go minus here, it's probably going to go plus here. Why? Because we see it's a polynomial. Polynomials do that stuff. We don't see any square roots in their absolute values or things of that sort. Cool. All right. I plug in 1, positive, positive, but negative. I plug in 3, positive, positive, positive. This is F prime. Now I say we make a rough sketch of this. Of F? No, of F. Don't you make a rough sketch of F? Yeah?
Mm-hmm.
Rough sketch of F. All right, let's see. What would F do? It would what? What's that mean? It went down. Then what?
Yeah.
Right? Right, very good. Yeah, goes up, go up, then what? Oh, then goes down. Then what? And when do x to the 4th graphs sometimes look like this thing? Like the debit? Yep, you bet. It's probably got a little. In the end, we'll sketch a nice picture. Get all this stuff out of the way. All right, let's fill in all the blanks. Now look at all that stuff. Let's crush it. Increasing. Look for the pluses. -2 to 0, where else?
2 to infinity.
All right, how about decreasing? -3 and -2, anywhere else? Can anyone read that? Harshman, is that okay? Yeah, okay. I know I got the writing from before, when I'm writing over there, I didn't want to make sure it didn't get mixed with the other writing. That's an infinity. I keep everything open parentheses. These are intervals. Now, you might use this to help you out. Where's the local max, or are there two of them?
There are 2. No, one, sorry.
There's one
At 0.
So there's one local max, you're saying it's at
0.
0. I'll fill this in a second, because that's key, we gotta know where to plug that. How about local min?
-10 and 2.
Ooh, there's 2, so I gotta put an extra space here on, that's okay. Then we got 2. We got a couple local mins. True? I have a sense they're probably gonna take on the same y value though, right? It's an even function, right?
Mm-hmm.
You know this.
So that's gonna be.
That even odd function does help out sometimes. Just because it's even, it means it's so reflective. So you're like, oh yeah, they're gonna take on the same, these are gonna take on the same y values. Alright, at 0 is local max, and where are the local mins? -2 and what?
2.
2.
Now, can you remember this? Where do I plug these now?
Original.
Gosh, you're good.
It's 12.
Seriously, very good. This is where, because it says, at x equal to their local max is, and you're like, I'm going to the original, the actual original, like this was a temperature function. What's the temperature? You know, it's like I'm gonna put that actual temperature down. The local max is, oh, I love plugging in zeros, that's easy, 12.
Why did you put on 0 if I actually looking for just the last of them?
Why did I use 0?
Yeah.
Oh, look at this. We know there's a local max, couple ways. One is the plus to the minus. That would mean the function did this. Look, I'll use my hand. It went up, increasing, then went down. And Josephine, I think just to remember that, I'll be honest, Josephine, some students just memorize plus to minus as max. I don't recommend it. I would say more conceptual. Think of a function like, use your hand if you have to, or make a sketch. Be like, it went up, it goes, we describe everything left to right. Left to right, it would do that. All right, hey, and when you want to use your calculator, plug in those 2's or do it in your head, I don't care.
-4.
-4 on both of them? Hey, can we already make a rough sketch of this graph then? We'll do second derivative, but can we?
Yeah.
All right, ready? Rough sketch. All right, we got to get rid of -2, and we got to get rid of what?
Positive 2.
All right, and -2 got to a what? -4. And 2 got to a -4. What's it going on at 0?
0.
Is it up at 12? And what's this graph do? Odd or even function, everyone? Even Steven, do you agree? That's an even function. Sure. Even Steve. That thing's even. Except my drawing's not that great. Sorry for my sloppy work. But it's even, right? Alright, cool. Hey, now let's get this done. Can I erase? I erase everything but first derivative because I need first derivative to get second derivative. What determines points of inflection and concave up and concave down? Oh, second derivative. So let me write it again. F prime was 4x cubed minus 16x. Give it a shot, everyone.
Square.
Awesome. 12x squared, and is there anything else?
Minus.
Minus 16. I think we're going to get a fraction out of that. Alright, let's just see. This is going to be interesting, and I want to know how you want to solve this. Claire, I wouldn't use quadratic formula there.
No.
Take out 4.
I wouldn't use quadratic formula on that, would you? No. We got easier ways. We know easier ways, but we're trying to solve for x equal to 0, right? Excuse me, this function set equal to, this portion is set equal to 0. We're starting to solve for x. So, I don't know, Kayla, I guess this would be one way. I could add 16 on both sides. Right? You would say, because a lot of you solve these this way.
Can we not factor or no?
You could, but you'd have to be careful. That's really a difference of squares. But you'd have to know what to put in that coefficient to the x of each one. Cool, I'll show you that in a second. If we wanted to see that, it'd be a difference of squares in terms of factoring. Okay? Now, this is one way. Now what could I divide on both sides? Okay, I'll show you that in case you prefer it. Can I reduce it?
Yeah, 4/3.
Yeah, when x squared equals 4/3. Kayla, what could I do to both sides now? Take the old square root. Now don't forget, there's something called the square root property. If you square root both sides of an equation, you gotta put a what?
Plus minus.
Plus or minus down. So maybe there's 2 points of inflection over here, because that would give us 2 possible points. Do you see 2 possible points of inflection in there? Right. Okay, that's what I mean. So it helps you catch this law. Don't forget the plus or minus. So x equals plus or minus. All right, that's one way to write it. I think we can improve that though, because a lot of you know the square root of 4.
2.
So are you okay if I leave this top numerator just a 2? I'll leave the bottom goofy. Now if you like rationalizing the denominator, go right ahead. That would be plus or minus 2 squared roots of 3/3, right? But that's okay. This is way better than that though. And you got a nice neat 2 up there. Now, these aren't points of inflection, but these are called possible. Maybe they are. How do we make sure, or how do we know it's certain that they're points of, we're going to check to see the concavity changes. So what test do we do? Second derivative test. Alright. Negative 2 over square root of 3, and 2 over square root of 3. Now where am I plugging these? If it's a second derivative test, where am I testing these? I test them in the second derivative. What's this going to tell me about? Concavity. Okay? So here, if you want, if I'm not, you might want to rewrite the second derivative equation right here before we forget. So you plug it in the right equation. What is the second derivative? It's that thing. Cool. Right. Who's got an easy test point in here?
0.
12 times 0 squared minus 16? Someone else, Daniel. That's a goofy looking number, everyone. You want to just use like 5?
2.
Yeah, 10. So they were like, what the hell? Just pick a big number. 100, and when it's 12 times 100 squared minus 16 positive.
Positive.
I mean, sometimes it's okay to just pick 1,000. You're like, yeah, 12 times 1,000 squared minus 16 will be positive. Do you agree?
Mm-hmm.
And what do you think?
That's positive too.
Keeps alternating. All right, so how many times did the concavity change?
Twice.
So how many poise we got?
2.
You want to just write it like this? Plus or minus? Okay. Remember, I said just listen. I'm okay if you just listen to x values. Unless you want to plug it back in there and write them as xy coordinates.
Yeah.
Ordered pairs. Web assign will make you do that. I just say listen to x values. Now, all the hard work's done, everyone. Where's it concave up?
So,
Right there. From negative infinity to
2.
anywhere else? Oh, so what should I put between them?
Union. And 2 root 3 to infinity.
Yeah, and where's it concave down?
Negative, negative 2 root 3 to 2 root 3.
Negative 2 over root 3 to 2 over root 3. If you want to rationalize the denominator, you can. Jessica, got all that? Yeah? Nice. Kayla? Hey, so you said, heck, I love these for difference in squares, back to those. But when there's a 12 in front, it makes it a little what? It makes it a little tough. So you have to make sure it be like this. I don't know if you're going to like this one. Ready? That factor? Square root 12x plus 4. Square root 12x minus 4. Would you like that? It's up to you though. Could I have factored it that way?
Yeah.
I mean, you could have. Who knows? There could be a student in this class who's like, oh, I like that better. Maybe it's Kayla, but it's someone in here. But I want to point out, it was a difference of squares, but since that's not perfect, I have to write whatever. Great. But look, you'll still get the same answer. X would equal negative 4 over square root. And then if you break that down, what are you getting?
That's letter 4 into 2 root 3, yep.
It's the same. It's the same number. Yeah. Cool. Oh, great job. Hey, last thing. I'm only do one of these, okay? Don't worry, we're gonna do a bunch more of these. Like you said, we gotta do some odds. We gotta do some. But I wanted to draw a graph of an f prime, and you and I are gonna try to analyze it.
Okay.
All right. We'll have to do both of these again next class, just to make sure you got it. All right, here it is. All right. Now, when I have to put a word up here, don't worry if it looks confusing to you, because this really is some abstract thought. You and I won't see any equation or anything, we're just looking at a graph, right? But if you know all the definitions, you'll be fine. If you know all the definitions, you'll be fine. Like definition of concave up. You're like, oh, that's where the slope of the graph was always increasing. Ready? And here comes f prime, okay? That's f prime. This is the x-axis, this is the y. And when you don't have to sketch f, but somebody in this class may try to help you better understand it and to answer questions, okay? You don't have to sketch f, but you may do that. That's why I put this above here. You might start doing some scratch work, okay? But this is the last thing. And you notice all my questions don't ask about f prime, but ask about what? F. But the only sketch I given you is what?
F
F prime, right? How about f as some points of a function? When you care if I write POI?
Mm-hmm.
F is conc up. F is conc down. Let's have some fun. All right. The first thing is max and min. Slope of graph was negative. Slope of graph was positive. So just the first thing I want you to think about. I'm just going to hold my hand. When was this graph below here? From here to here, right?
Mm-hmm.
Where else? From there to there. Now I'll just put some numbers down. How about this is x equal to like -6? Right here when x equals -3. Right here x equals 2. Right here x equals 5. Right here x equals 7. And I'll just put an arrow and an arrow. Alright? Now, when is this graph below here?
Negative
Up
infinity.
to -6 and then where? 7. So we're saying we know something about f. F was decreasing. F was going down. Prior to -6 and where else?
After -7.
After 7. Now what was the graph doing between -6 and 7 the entire time? It was what?
Fluctuating.
It was going up. It was increasing. So I mean that's really what's going on. I mean, this is down. It's like I know this graph's like it went down to -6 right there, but then between -6 and 7, what did the graph do? And it kept going up. It kept going up, and then when it got to 7, it started to do what again?
Going down.
And look how sloppy this is. I don't care if it's sloppy right now. I can improve it, but that's the sense of this. This graph went down. Then it kept going up, going up, going up, going up, going up, and then right at 7, the slope went what? F prime is negative, that means the graph is what? Going down. Alright? But see, that's not the graph of it, but I can improve that. Does that make sense?
Mm-hmm.
But what's key is, I think we know how to identify the local max and min right away. It's when the first derivative equals 0. So for local max and mins, get your eyes right on this axis right here. Do you see any place where the first derivative equals 0?
Negative.
All right, here's one. Now you might use your hands to do this. That would mean, watch me with my hands, that would mean the graph did what? It went from decreasing to increasing. Right? Slope was negative, and slope was positive. So that's a min, isn't it?
Mm-hmm.
Does that make sense? Plus, you might do this to help you see that. So there's a local min where? -6. Now you know what is it? We can't answer that, right? So how about we just leave the axis? I'll take that part off my mom. We don't know enough to put those in, right? We weren't given an equation, so I can't ask that. Where do you think there's a local max? We got two options. Is this the local max? Let's think about this. The graph was positive, graph was 0,
Mm-hmm.
then graph is positive again. That's not a max. Do you all agree?
Mm-hmm.
Think about this, right before. It's just think above the x-axis. I know it's abstract. Above the x-axis, graph was positive, graph was 0, slope was 0, and then it was positive again. So that's not a max, but how about here? It was positive, then it was what? Negative. Oh yeah, there it is. What's that next value?
5.
7, right?
7, sorry.
And this is for f, right? Local max, I'll say of f. Now, we'll nail these. Everyone for increasing? Behind this? Where is it above? Go ahead and do it. From -6 all the way to what? 7. But I think it's a good idea to write it like this. How about let's go from -6 to 2. And then we'll put a union from what?
2 to 7.
2 to 7. No, people always wonder, like, would you mark off if I just wrote -6 to 7? I'm pretty nice there. You know? But isn't it really, keep it simple, it's where it's above that x-axis?
Uh-huh.
Because the slope is what? Right, positive, it's increasing, you told it. And where's it decreasing?
Negative infinity to -6, and then
And then when it was underneath this, right?
So 7
F
to
prime is
infinity.
negative. To do this, we're just going back to the definitions. But don't worry, if you're sitting right now and you're going, you're staying silent, and you're kind of like, this stuff's a little weird. It is abstract because we don't have any equation to deal with, do we? We're just going based on conceptual ideas, right? This is conceptual understanding. It's decreasing where else?
7 to infinity.
Now, points of inflection, this is my favorite. Edwin, would you just look for the hills? Josephine, points of inflection. And this F prime graph, would you just look for the hills?
Yep.
You go, why? Because that's where the concavity would change. That's where second derivative would change. If this is F prime, then where does F double prime change? Wherever I see a hill.
Negative.
Oh, there's a hill, boop. Point of F. I love these. Where else is a hill?
Two.
Oh, right there, point of F. I love these. It's so easy to find points of inflection on an F prime graph. It's where it's where second derivative changes. Okay, if this is first derivative, just see where we went up to down, or down to up. Where else is there a point of F?
At 5,
So how many points of inflection are there?
3.
At x equal to
Negative 3,
-3, comma
2,
2,
5.
and comma 5. And now we can do concave up and concave down. Because where's the concave up? In between these.
Yeah.
You know? Concave up, remember second derivative is what? Positive. Well, this is a first derivative. So just look to see where the slope was from. Concave up. Concave down. Concave up.
Ah,
So where's the concave up?
so
From
negative
negative infinity to the
-3.
-3. I'll put a union anywhere else.
2 to 5.
2 to 5. And where is it? Concave down. No, just the opposite. In between these points of inflection, it went concave down from.
-3 to 5 to infinity.
Now, Emma, trust me, I know this topic. Years and years and years of teaching calculus. I can have the student who hates algebra, they love this stuff, right? Or vice versa. The student is just awesome at algebra, and they say, I don't like this stuff. So I understand it. So I'll make sure next class we do another one of these, okay? It's all going back to definitions, but there's ways you can figure out, you can know what to look for. Like my favorite's the points of inflection on F prime. It's just going to be where it was. It goes like that, it goes like that, right? And great job. Have a great weekend. I'll make sure our next class, we'll do some more of those, then a little bit, a little more complicated stuff. Have a great weekend.
So